My name is, oops. All right. Okay. Yeah. So, hello, I'm Joachim. I work at the in the GrowAI team here at ITU, a team led by Sebastian Risi, which some of you might know. So I named this talk Neurons, Synapses, Meta-Reinforcement Learning, and Collective Intelligence. And for anyone who might think already, whoa, this will be all over the place, if I can give, maybe I cannot. No, nothing much is happening here. Okay, I can. All right. So yeah, if I were to condense the message of this talk into one sentence, it's that we can look at artificial neural networks as collective of adapting agents, or more precisely, that I would argue that we should change the way we structure networks from what artificial neural networks from what we're currently training them into something where this statement is actually true. So the topics that I'll be touching upon here is first and foremost structurally flexible neural networks. This is where I'm going to spend most of the time, simply because this is what I'm mostly directly working with, and I'll try to connect this to these other topics of meta learning. I'll introduce the symmetry dilemma, modular neural networks for robotics, and multi-agent reinforcement learning. And so I was particularly happy that I was invited to talk here, because I think that there have been some different branches in the area of collective intelligence that has for a while now matured a bit on their own, and I think in the very near future it's like these different branches can be ready to be unified, and so I'll give my perspective on how we can think of them, their challenges and their opportunities in a cohesive way, and build something together out of several branches. All right. So I should say that some of I've taken major inspirations from existing literature. Of course, I would especially point towards the Collective Intelligence survey by David Ha and Eugene Tang, and also self-organizing and self-assembling blog by my supervisor, Sebastian Risi, both from a few years ago. So, all right, structurally flexible neural networks, evolving building blocks for general agents. This was a major part of my PhD thesis and work afterwards in my as my work as a postdoc. So the goal here is, can we optimize neural network parameters in a way so that they can be used to solve tasks that have different structural requirements? So usually when we train artificial neural networks, it is bound to whatever input-output space that we trained it in originally. But it could be useful for us if we could train the parameters in a different way so that the same set of parameters can solve multiple tasks. Why would we want to do this? I think there are a bunch of different reasons that are good for, but I would like to highlight just two here. So one, it could be the adaptation to varying robot morphologies. Maybe we train first our parameters in a base robot setting. If we then want to add some actuators or sensors to the robot, it would be nice if we didn't have to start all over with our optimization. And there are some different approaches to this particular problem, and I will touch upon some of them later and tie them into the flexible networks. But what I particularly is very interested in is the idea of meta-learning across a diverse set of tasks. So meta-learning, or learning to learn, has to do with not finding one particular policy, but finding out, learning to learn more policies in a rapid manner. And as is the case with all across machine learning, the more diverse set of training set that we can have, the higher could our expectations be to something that generalizes better. And right now, we're constrained in how diverse our training set of tasks can be, in that tasks usually need to all have the same input and output space. But if we can increase this, we might expect more general learners. And I would say, so as a note to this, like a lot of time when you start reading about meta-learning, the underlying assumption of what a meta-learner has to learn is one underlying representation that can be reused within the distribution of tasks to bias the learning that it has to do in that task distribution. I think if we can widen the set of tasks that we can train on, we can be a bit more ambitious and actually have a meta-learner that only exploits the fact that there is something that can be learned in the tasks. So how can we achieve something like this? Well, one idea is to focus on modular units. So make general building blocks instead of go directly to one or lock ourselves into one architecture from the beginning. So if we imagine traditional MLP, yes, we think about it in terms of being built out of synapses and neurons, but there's no real good way of taking any one weight or synapse out of that network and build something else with it. There's not a great way to just take any scalar weight and say there's this scalar has some general property. I can reuse it somewhere else. So instead, what we want is to actually have parameterized building blocks that we can then assemble into different network types. So how we get there? We first take a detour to think about synaptic plasticity and black box meta-learning. So again, meta-learning, we want to rapidly find a function or working policies across different tasks. We're not looking for one specific policy. When we learn a meta-learner, we're trying to know how to learn quickly. So one paper that is similar to this field and which I think to this day is one of the most interesting papers in artificial intelligence is this paper by DX Wang et al., Learning to Reinforcement Learn, where they showed that an RNN, such as an LS long short-term memory unit, can be optimized to implement their own reinforcement learning within their dynamics. So we call this black box reinforcement learning. And the requirements for getting for implementing an RL algorithm in its own dynamics is simply that we, one, train the LSTM across multiple different tasks, but also that in addition to its observation, get at input at every step the reward that it got in the last time step, as well as the action that it took to get that reward in the last time step. So if you give it this information, it can actually learn to implement it. So you can optimize it with any optimization function, the parameters of the LSTM itself, the gates of the LSTM. But if you provided this information and optimize it across different tasks, then it can actually learn in new tasks that it didn't see before to optimize the reward on a much faster time scale than the original algorithm that was used to optimize the gate parameters. So for example, using evolution or using backpropagation, which can be very sample inefficient and very slow. So this was one very exciting way of getting something that can learn something new, a different way of achieving something similar is through synaptic plasticity. So let's see if we can have it keep playing somehow, no? Okay, this doesn't seem to work very well. Anyway, what we should be seeing is on the left here, we see an agent that is can I even? Well, that is unfortunate. Yeah. Is there a good way to do that? Because it did. Oh, okay. Yeah, sorry about that. But so I can see say in the meantime that instead of training the weights of a neural network directly, what we could train is a set of update rules that will change continually the weights of that network. And that is what hopefully we can see some depiction of, but it keeps stopping for some reason. But if it was a bit, and now we see that here, an agent is following a track that it has never seen before, and the weight keeps changing throughout. In the other video, which probably also will have a hard time working, no? Huh. We see that with a similar approach, and a network that, I can show it one more time maybe, a network that is static, that doesn't have these plastic components, it fails whenever like in a new setting, in a morphology setting that it didn't see during training, whereas the Heppian network takes some time to adjust in the beginning, and then it moves much better than the other result. So what is happening here is that for every weight we have a simple what we call a Heppian function that is parameterized and that takes in inputs which are the activations of the neurons that each of the synapses connect, and use that information to connect the synapse. So these are two. This is not working with me now. All right, so two different ways of doing some kind of meta learning. But both of them only work in fixed structures. So for the Heppian rules, they're all tied to, they only make sense in the specific context that they were evolved in. We cannot extract the rules and put them into a different network, because each of them is uniquely defined by the position that they're in as well. And the same with the LSTM here, it is fixed to whatever input and output size that it was trained to. So one idea that we might get then is, can we merge these two methods? So instead of having a bunch of unique rules in the Heppian setting, can we take this RNN structure that we know can learn to update itself in an adaptive way on a fast timescale? Can we switch all the unique simple rules out with one single parameterization of this kind of RNN agent that we know can exhibit meta learning on its own? So there are some people who have done this. I've been particularly influenced by the work of Louis Kiers, who does something almost to the point of what I described, where building networks consisting of RNNs. So we build a larger network out of smaller networks that crucially share their parameterization. So, for example, point over here maybe. So here we have a shallow network where each of the connections are expressed by the hidden state of an LSTM with shared parameters across all of the synapses. So the important thing to note is that the hidden states are not shared. It's only the parameterization that updates the hidden state, right? So they are able to express different values for each of them, even though they have the same parameterization across the board. Okay, so why is this useful in the context of structural flexibility? Well, to achieve a structural flexible network, we need some properties. We need to have invariance to permutations of inputs and outputs, and we also need to have the property of being invariant to the size of the inputs and outputs. And these are indeed different properties. In practice, they usually go hand in hand when we solve or when we get the solutions to have these properties. But the most important thing is that no parameters can be optimized relative to a single fixed position in the network. And there are some more details that are more specific to permutation invariance, which I won't go into here, but which was also led by David Ha and Eugene Tang. Again, important thing to remember is no parameters can be optimized relative to one fixed position. As soon as we do that, those parameters will overfit to that exact position, and we will not be able to use them in any other context, right? Having this shared parameter RNN across all of the edges here, it does actually achieve that because there are since the parameters are shared across, none of them are only optimized to one particular fixed point, right? So that is great. We have a solution to the structural flexibility. However, it turns out that it's not quite without problems to optimize a system like this, and this is where the symmetry dilemma comes into play. This is something that we have end up referring to as the symmetry dilemma, and is one of the main causes of difficulties to create these types of networks. So I'll explain this really quickly by starting by saying that what we mean by a symmetric parameterization is exactly that any parameter in the network can be switched out with any others without changing the function. So again, this corresponds to that this is in accordance to the statement that no parameters must be optimized relative to a specific position. Those two are kind of saying the same thing, but one is expressed using the asymmetric terminology. All right, so if we think of a trivial example, this is what I found to be the easiest to explain why this is a problem, or why that constitutes a problem is, okay, so if we imagine a fully connected MLP where all weights have the same value and all the biases have the same value, this is obviously a very symmetric network. We can change, we can switch out any of the parameters there and it will still look very much the same, but it's not useful for information processing at all. So yes, it gets us our properties that we need for structural flexibility, but we also cannot use it for anything. And there's not any way for us to optimize out of that when we are locked into the notion of all the weights must share the value. There's no value that we can find that will escape the fact that when all the weights are the same and the network is fully connected, already in the first layer after the input layer, all the neurons will have exactly the same activation. And so there's no distributed information in the network at all. All the outputs in the end will end up being the same. We have not found something useful at all. So this is when we try to induce symmetry into the direct encoding of the network. So directly into the weights of some network. So more... And make it more clear, the symmetry dilemma here is, so on one hand, we want to achieve the structural flexibility that symmetry provides, but on the other hand, we need to maintain a structure that is capable of having distributed information across all of its nodes. Like I said, this is I would say, near impossible dilemma to overcome in the direct encoding space of a neural network. So instead, we try and do this as an indirect approach. So again, we're not our parameters in our indirect encoding are optimized in a symmetric manner, but these functions are supposed to output weights, a direct encoding that is not symmetric anymore, right? And so this type of structure does achieve this, but it's still not without danger of even when all of these hidden states of the RNNs can have different hidden states. there's still a constant risk of them converging to the same value, especially if we have deeper network structures. That risk increases with each new layer in the network, simply because of the fact that when we have a function that has the same parameters, if at any point the inputs to those functions become very similar, they will output something that is very similar. And that can kind of create a downward spiral into converging to the same thing. And we end up again with a direct encoding that is not useful to us. This is where I'm going to then draw the first parallel into multi-agent cooperation, because in a lot of multi-agent settings, we might have agents that share their policy networks. The reason why we would have agents that all have the same policy net is, again, a question of flexibility. We might not in the future know exactly how many agents we would need for tasks in the future. Maybe some tasks, some exploration space need 5 agents to be covered in an efficient way. Another might need 10, and so on. And so in such cases, it's normal to have just one, to try to train one policy that can learn to update its parameters on the fly, instead of having to try to optimize a new policy from scratch every time we need to add a new agent. So very much the same problem. However, it's not usually it's not usually as a big issue in this setting, although the principle seems to be the same. So why is this? Well, it's not agents typically are embodied in some kind of space where they have different positions. Different positions will keep providing the agents with different inputs, and it will make their behavior differently. So it's not usually the case that we put all of our robots in the exact same spot where they will get the exact same inputs all the time. There is a natural source of different information flow, or a differentiated information flow that also can help maintain the behavior from collapsing into the same thing. Can we use a notion like this in the to solve our problems within the neural networks? So this is where our work comes into play. This was published actually last week at the Gecko conference. So yeah, super new. But we cannot really our neurons are not really embedded in a 2D space like the one I showed with the robots before. They don't have some Euclidean space that are meaningful to them, but they are all embedded in some graph. So one way of changing how a notion of precision is to change the connectivity. So a way of breaking, I should say, in this particular model, all the edges are, again, hidden states of RNNs. Edges that share colors share their parameterization. As we can see, there is a notion of different layers that have different colors, and therefore the parameterization is increased a little bit compared to having a fully only one type throughout the network. This is one thing we discovered while working with these types of network, that even though it's not completely symmetric in the way that I introduced before, it's actually fine as long as the symmetric properties are preserved layer-wise. We can still have the same structural flexibility properties that we are looking for. So we break the symmetry by having a random sparse connectivity and by having random hidden state initializations. So all the weights start out with random values and have to then be updated by their respective by their RNNs. So we optimize the RNN parameters with covariance matrix adaptation. Yes, this is a powerful evolutionary algorithm when you have a small parameter space. And because the number of RNN parameters are not tied to the number of neurons that are in this space, we can optimize them across different structures. When the networks are initialized with random weights and random connectivities, then the RNNs must quickly update weights to make the network going from a random one into a functional one. And this requires some interactions with the environment. And the fitness is or the way we trained is these parameters is reflected in this fact that a lifetime of parameters in this evolutionary setting is not running just one episode of the environment that it's in, but multiple ones, as we shall see here, if I'm lucky enough that the video works there. So a lifetime of the agent is we take a random initialization. I'll just stop it here while I explain. So we take a random initialization, put it into different environments, and then we let it, so in this particular case, we let it train for 8 episodes. So in the beginning, if we look at the card poll, it has to score as high as possible. It has the first 2 attempts here was not really successful. It had a completely random network. It doesn't even have any notion of what of its output corresponds to what action, because everything everything could be switched out with everything. The only way for it to get this information is through interacting with the environment. So at first there we see it doesn't do so well, but pretty quickly after just a few attempts, I think it will speed up in just a second, it already becomes functional. So we see this is an episode where it does well. And so I'll just stop it again. So one evaluation of parameters in our setting here is then across the 3 tasks, each of them in 8 episodes. The number of episodes could be more or less. That depends on how hard we expect it to be to find good solutions quickly in the particular environment. But this is something, that I was really happy to see, that we could actually have the same set of parameters do well in a very few attempts across multiple tasks that do not share like an underlying input-output space. However, if we, if we try the same in a continuous task, things do not work quite as well. This is much harder to do, almost as hard as making this video work. And of course, it makes sense that that it's harder to solve continuous tasks rather than I'll give it 2 seconds, rather than discrete ones, because the coordination of the output units has to be much more precise, right? When we in discrete action spaces, we don't really care about the exact coordination as long as the right action has the highest value. Continuous tasks, it does find a way to move in the environment if we could just okay. I guess you'll have to trust me on that one, but it doesn't work in a way that we would hope. So it finds some way of breaking the physics and actually just float a bit around. So not really finding a very satisfactory solution. But there has luckily been done work that is similar to what we are trying to achieve, but directly on a continuous robot. So here, the same idea about learning modules is present, but the modules, instead of being on an arbitrary computation graph, each different module that we try to learn is tied to a specific component of the robot. So there are a few different iterations of this kind of research. This one I liked in particular by Whitman et al., where they have 3 different parts. They train modules so small controllers that are also neural networks for each of these, and then copy them as many of time they need for that particular robot structure that they have. So this is a way of using some of the same idea as being able to generalize across morphologies without having to retrain every time we're changing our morphology a little bit. Of course, this kind of approach only works when we have something like a structure that is embodied and can meaningfully be divided up into parts. But if our end goal is to have robots that work well in the world, I think this is a reasonable constraint. So we have I've gone through 3 different settings that have some of the same underlying structure, in that they consist of modules that have a shared parameterization, and they have different ways of breaking the symmetry. The hardest case, I would say, is in this indirect encoding space, where neurons are not really don't really have access, or the hidden neurons don't really have access to any environmental information directly, which is the case with these robot modules, as well as the robots themselves, actually. Yeah, I don't have the time to go over this, but I do want to address another problem that is more pronounced also in the multi-agent case, which is the credit assignment problem. So if we now have a setting where we have different agents and only some of them contribute directly to the fitness of the final goal. So say the robots here, they have to pick something up, they have to search, they have to do some kind of foraging task, but they have some helpers, which are these submarines that can do explorations for the robots. So the submarines don't directly influence the fitness in that they don't pick anything up, and that is how the group is evaluated. But we would like to have some way of assigning credit to them anyway, because they can help out the other agents, right? And there is a rich, this is a problem that is very prevalent across the field of it's not so important anyway. No, but this is a fairly this is a very active research field on its own, to find ways of assigning credit to agents that might or might not directly influence the the evaluation metric. And this is exactly the same problem that we also have in the in neural networks, where only the output neurons directly influence the fitness, and all of the hidden neurons only indirectly contribute to this. So one thing is to break symmetry in a computational graph by changing the input that each of them get, but if we want them to course correct somehow, maybe they can inference what they need to do to course correct it only from the surroundings alone. But when we're using this kind of black box meta learner, one of the important components is to be able to give it an as accurate evaluation metric as possible at each time step, so that it can better learn to associate specific actions with specific outcomes. Especially when we're in a network, it's very hard to infer anything just from input environments, regardless of how big of an effort we do to make the positioning and therefore the input to each of the modules different from each other. So yeah, here at the end, I think there are some great opportunities in combining some of these methods. So as we saw, we have the modular controllers. They're pretty good at working with across different morphologies. but they don't really have or their computational capacity is kind of also bound to the specific morphology that they're in. It's the size of it is completely defined by the robot morphology itself. But we could use this could easily be combined with a structural flexible approach that could kind of be the central nervous system to those modules that does more local computation and when which do exploit some structural information that is not really present in the structural flexible networks. So the framework is we can take this small unit that is the black box meta learner, and we can instantiate it as the main building block, both in the robot modules and as arbitrary computational units. And this can constitute brains of agents in the multi-agent settings. Some of the challenges that arise when try to update multi-agents here, like the credit assignment problem, is exactly the same problems that we find here, just at a different scale. So when we find good solutions to this problem, they can be transferred from the level of their collective organization to the collective organization that comprise each of these artificial brains. So I think also that is all the time that I have. So I'll say thanks for listening. I don't know how much time we have for questions, but otherwise, I'll be happy to chat with you after, or you can send me an email. I'd like to thank my GROI group that I'm part of, who are also working really hard to make solutions on these type of problems. So thanks.